You know how sometimes you go to bake a cake, but your bananas have all gone rotten, your utensils have rusted, you trip and pour all of your baking soda into the vinegar jug, and then your oven explodes? My friend, you and your chemical reactions have fallen victim to enthalpy and entropy, and boy are they forces to be reckoned with. Now your reactants are all products. So what are these E words, and what's their big idea? Let's start with enthalpy, an increase or decrease of energy during a chemical reaction. Every molecule has a certain amount of chemical potential energy stored within the bonds between its atoms. Chemicals with more energy are less stable, and thus more likely to react. Let's visualize the energy flow in a reaction, the combustion of hydrogen and oxygen, by playing a round of crazy golf. Our goal is to get a ball, the reactant, up a small rise and down the other, much steeper slope. Where the hill goes up, we need to add energy to the ball. And where it goes down, the ball releases energy into its surroundings. The hole represents the product, or result of the reaction. When the reaction period ends, the ball is inside the hole, and we have our product, water. This, like when our oven exploded, is an exothermic reaction, meaning that the chemical's final energy is less than its starting energy, and the difference has been added to the surrounding environment as light and heat. We can also play out the opposite type of reaction, an endothermic reaction, where the final energy is greater than the starting energy. That's what we were trying to achieve by baking our cake. The added heat from the oven would change the chemical structure of the proteins in the eggs and various compounds in the butter. So that's enthalpy. As you might suspect, exothermic reactions are more likely to happen than endothermic ones because they require less energy to occur. But there's another independent factor that can make reactions happen: entropy. Entropy measures a chemical's randomness. Here's an enormous pyramid of golf balls. Its ordered structure means it has low entropy. However, when it collapses, we have chaos everywhere, balls bouncing high and wide, so much so that some even go over the hill. This shift to instability, or higher entropy, can allow reactions to happen. As with the golf balls, in actual chemicals, this transition from structure to disorder gets some reactants past the hump and lets them start a reaction. You can see both enthalpy and entropy at play when you go to light a campfire to cook dinner. Your match adds enough energy to activate the exothermic reaction of combustion, converting the high-energy combustible material in the wood to lower-energy carbon dioxide and water. Entropy also increases and helps the reaction along because the neat, organized log of wood is now converted into randomly moving water vapor and carbon dioxide. The energy shed by this exothermic reaction powers the endothermic reaction of cooking your dinner. Bon appetit!
The hot ice experiment. Hot ice refers to a popular chemical demonstration in which a solution of sodium acetate is dissolved in water and placed in a freezer, instantly solidifying when poured from its container, or when a single crystal of solid sodium acetate is dropped into the solution. The solidification process releases heat and thus gives the appearance of the formation of hot ice. Chemistry instructors use this to demonstrate the phenomenon of supersaturation, or the ability of some solutions to contain more dissolved material than they normally should. All combustion reactions are exothermic reactions. Falazole. Acetone melts styrofoam because it is a very good solvent for polystyrene. The material that styrofoam is made from. Polystyrene is made from the monomer styrene, an organic compound which is catalyzed and turned into polystyrene, a solid plastic which is readily soluble in acetone. If bubbles are introduced into the polystyrene, you get styrofoam. So since the basic ingredient in styrofoam is styrofoam. Have you ever played with a black snake? It's a firework. When lit, it smokes and creates ash resembling a snake. The instructions are: for step 1, mix 4 tablespoons of sugar with 1 tablespoon of baking soda. Step 2 is, using the sand, create a mound and then a depression in the center of the sand mound. Step 3 is, pour some of the isopropyl alcohol into the depression. Step 4 is, pour the sugar and baking soda mixture into the depression. Step 5, using the grill lighter, ignite the sugar and baking soda mixture and observe. Carbon snake is a demonstration of the dehydration reaction of sugar by concentrated sulfuric acid. Carbon snake experiment can sometimes be misrecognized as black snake, sugar snake, or burning sugar, which involves the reaction with baking soda instead of sulfuric acid. Very cool experiment. Two dry solids, barium hydroxide and ammonium nitrate, are mixed to produce an endothermic reaction. Endothermic reaction meaning energy is taken in from the surroundings. The surroundings then have less energy than they started with, so the temperature falls. The temperature of the mixture drops approximately 40 degrees Celsius and is cold enough to freeze the reaction beaker to water on a block of wood. To conduct this demonstration, place a drop or two of water on the wooden block. Place the container on top of the block of wood, covering the water. Mix two solids together in a beaker. Stir for a few seconds with a stirring rod. The mixture should become moist from the water released by the barium hydroxide. Do not add any water to the beaker. Look at the temperature while stirring the chemicals. The mixture will become extremely cold and freeze the reaction beaker to the damp block of wood. The entire block can be lifted up by lifting the beaker. However, while we conducted the experiment, the beaker cannot lift up the wooden block since the weight of the block is heavier than the beaker. Yet you can see the moistness on the surface of the beaker. The moistness is from the chemicals. This reaction releases NH3 or ammonia gas. Students may be able to detect the odor if they are close enough. Silver mirror. So the steps for the reaction are as follows. Ammonia is poured into the beaker and some sodium hydroxide is added. Look how the sodium hydroxide dissolves in ammonia. A small amount of this mixture is added to a test tube containing silver nitrate solution. A brown precipitate is formed. Add more ammonia if the precipitate hasn't dissolved yet. In another test tube, a solution of glycerol is prepared. The two solutions are poured together. Hot water is put in a large beaker in which the test tube is heated. A thin layer of silver is formed inside the test tube. Starch and iodide solution. In this article, you will learn how the reaction of starch and iodine takes place. This chemical process is not only very interesting, it is also practical, as it is often used in everyday life when we need to find out whether a certain product contains starch. To start with, let's define what starch is. It's a tasteless white powder resembling flour on its consistency, and with a formula, a polysaccharide of amylose and amylopectin. The structure of amylopectin. Starch is the result of a natural process, known as photosynthesis. For plants, it serves as a supply of nutrients, and for the human body, it serves as a supply of important carbohydrates. Starch interacts with iodine, forming inclusion compounds or clathrates. Inclusion compounds are special compounds in which the molecules of one substance enter the molecular structure of another substance. In this case, amylose molecules, one of the main polysaccharides of starch, will be the host and the iodine molecules will be the guests.